All right, so welcome to the class. Today we're gonna discussing the random variable topic. So last time, remember we talked about single random variable and how to compute a single random variables, their expectation and variance if they're continuous. So today, we'll consider what about two random variables happen all together. So in that case, like let's think about x is a random variable and y is another, and maybe z is a consider with them all together. So we have to consider the distribution of three random variables. So intuitively, if there's one dimension, it's like xy coordinate can describe that well. But if it's two-dimensional, well, the z axis will add it on. Three-dimensional, which is a four. If there's three random variables, then it's a four-dimensional graph, which is impossible to be graphed out. Okay. And thanks to Alexander Giesing, and he's now not in the University of Washington. He's not in it here for the future, but he's still like provide me with the lecture notes and the lecture slides that I can use. So thanks for him again here. So today's lecture will begin with the joint distribution. That's like multiple random variables are all considered all together. And also we'll see another fun topic, which is what's about independence between different variables. Okay, so that's the two main topic for today. So let's say why we want to study many different random variables. Why study them all together? So because let's think about some examples. If you want to predict SP500 is like an index and IBM stock is a stock. What about if we want to compute them all together, want to consider them by as one single random variable or consider their motion in the Brownian motions model to see how one is influencing the other. So in this case, we might use two random variable, one describing SP500 and another describing IBM stock. So we can see how they're distributed and find some correlation in them with statistical knowledge. Okay, and some intuitive question we ask is like, how can we say two independent? So they're not correlated, or they have no relationship, no causal relationship, or we can think about that, or how to compute the expectation and variance of several different random variable. And that's very interesting topic to consider about, and we will explore today. Okay, so first let's define a joint event. So give some very simple idea. It's about like tossing dice again. It's like if you roll a dice, now we roll two dice, so there are totally 36 possible outcomes. So joint event is like is you can see it as an ordered pair, as S is the first coordinate, M is another coordinate, as you can see here, right? And in this case, we'll say, well, S was S. It's a sum of the two periodized rolling, and M is the maximum. So let's consider what's the range of S can be, or the sample space is X. S is sum, and the dice is from 1 to 6, so it must go from 2 to 12 because the minimum is like two dice are both 1, and maximum is two dice are both 6. So this is like the S distribution. The sum of two dice distribution is likely here. And for M is the maximum, so it can only be 1 to 6, and this is the distribution of it. Okay, so we define the joint event as the ordered pair sum and maximum equal to AB. And this means like it is an intersection, which means S the sum must equal to A and M must equal to B. And A is chosen from 2 to 12, B is chosen from 1 to 6. Okay, so we need to describe how probability mass is distributed over the range Sn. So now here it only have like 2 to 12, which is 11 values, and here it has let's say 6 values. So totally, if we do a like ordered pair, it will have how many values of it? It will have 66 values. However, some of the value might be 0 because you might consider like if the maximum is 1 and its sum cannot be 12. So 1, 12 doesn't make any sense here. Or 12, 1. 12, 1 doesn't make any sense here because there's no dice which like maximum because 1 and 1, the only case is the sum is 2, so it's not 12. We can also think in this way. All right. So let's see what's actually look like for the mass function. Because this is discrete, it has a finitely many values, so it's this discrete function. So what's the graph is actually look like? So we consider like two-way table. Maybe it's you can say a two-way table. The first coordinate is n, which is maximum, and the second coordinate is s, which is the sum. All right. So let's think about it. So the probability mass function, which is s must equal to a, and at the same time, maximum must equal to b. So here, the first column, let's say the first column here, which is this column. So in this case, we can see it's 1/36 because there's only one case where the maximum 1, 1, and the sum is 2. And all these are impossible, so it goes to 0. And when the maximum is 2, there's two cases, like if it's 2, 1, 1, 2, or 2, 2. So this corresponds to 2, 1, 1, 2 corresponds to sum is 3, and 2, 2 corresponds to sum is 4. And it all goes the way to this case. And we can see how many of the entries here. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it's 11 entries in the vertical in the S dimension, and there's 6 entries here, which means there are totally 66 entries as we just find before. So but many of them are 0 because there's impossible, or there's no probability that for example, the maximum is 5, but the sum is 2, because one of the dice, which is the maximum, is already overvalued 2. So this is only possible values here. And this is our new sample space. But you can also say this is a new sample space with some values just probability equal to 0. That's totally fine. Or you can say it's just the totality of R Cartesian product with R, like R2 squared. That's our how to say sample space. That's also fine because beyond that it just goes to 0, right? Okay, so let's see some definitions of like several random variables. So previously we have find like how we define a single random variable. It's like, okay, so single variables like px is distribution is when all of the outcomes in A, right? And for the several random variables, like multiple random variables, we say x1, x2, x3, x4 to xn. And now in this case, the probability distribution px now is becoming like px1 to xn. And probably can also denote as px, because if it's like very clear in the question how we know just like x is a simplification of x1 to xn, then we can use it. And it's denoted as x1 to xn belongs to set A. And A here is not like, it's not R anymore. A is R to the power of n, which is Rn space. So we can use a graph to illustrate it here. Like for example, if there's a two-dimensional, here Rn is R2. It's a R2 space. And now in the topological scale, we can say A is a ball. Is a closed ball or is open ball, but probability is usually if it's like continuous, probably open ball, closed ball, not very not very serious to think, because if the boundary doesn't contain any value because it goes to 0 when we only consider the boundary of some balls. So let's say it's an open ball A. And in this case, like all the value must x1 belongs to here, x2 belongs here, and it forms like a elliptical shape. And the function is like the omega goes to R2, which is like each outcome goes to a set in R2 that x1 omega and x2 omega, or the outcome is just inside the set A. All right, then what about its mass function? So for discrete random variables, its mass function can easily be seen, which is very similar to what we did before. If we just change the belongs to A to be a certain value, then it means the like a single equation in the mass function. So here, let's say Px is equal to the probability that for each outcome in the sample space, X take the outcome to value X, fixed value X, which is P capital X equal to X. So this is the probability mass function we defined before. But for joint probability mass function, this is simply called probability mass function PMF. And now it's the JPMF, which is joint probability mass function, have multiple random variables. So here, it must like x1 equal to x1, x2 equal to x2, and capital Xn equal to Xn. So all of the values in each dimension must equal at the same time to satisfy Pxs right here. Okay, and this is called a joint mass property mass function. And sometimes it's convenient to extend Px to a function defined on all of Rn by setting other when it's not in the sample space but still in Rn, it's just equal to 0, as I said before here. Okay. And there are some consequences of it, just like what we defined probability density function and mass function before. The sum of all of the value vector x belongs to the Rn space is equal to 1. By summing up all of the single single probability equation, it must belongs to 1. That's the definition. So this must follow. And the top one also need to follow too, because let's say and all of the probabilities part is non-negative, at least it must be 0. So here you say Pxx equal to Px1 xn, x1 to xn must greater or equal to 0, and this is true too. So for all of the x inside this one, which is r to the which is like r to the power of n, r in the Rn space, must greater or equal to 0. This is also true. And for the third property, it belongs to the probabilities third property as well. It's like it's countably adaptive, countably additive. So what does that mean? That means like the probability of x when it's considered a sample space A. And this belongs to, well, let's think about it. So this notation denotes like the ordered pair, or we say the n-dimensional vector x1 to xn belongs to the set A. And this is just equal to, we sum up all of the possibilities of that if x1, xn, their combination of a single vector is in A, which is equal to the summing up. We rewrite this equation as this equation. Okay, and it belongs Pxx, the PMF sum. So this is equally likely to say, well, the joint probability mass function is also countably additive, because each of the Pxx, they are disjoint to each other. All right. So let's give one example of the joint PMF. So still the same case. We consider one random variable as the sum of the two dice and another is the maximum. So now we want to see we see this graph before and we know its definition. So our question on to ask is like, what is the probability that the sum is equal to 7? So what about we consider the sum is 7? We don't need to consider what m value is. So we just see what values brings the sum of two dice rolling equal to 7. And in this case, we just go through the horizontal line of this when s equal to 7. So we find it's 0, 0, 0, 2 over 36, 2 over 36, and 2 over 36, which is 6 over 36 equal to 1 over 6. So x equal to 7 is just like x equals 7, maximum equal to 1, union with x equal to 7, maximum equal to 2, union with 3, 4, 5, 6, the maximum equal to 6. So, and because all of these cases are disjoint with each other by the definition of the PMF, and then we just need to sum up those values by the countably additive property of joint PMF. And at last, we find out this value. So this is our intuitive cases. And what about, another example might be we want to see, what about two dice rolling and maximum is equal to 3? So we just see this, we just ignore the s dimension and go through the m's dimension and find, oh, 3 is here. And we sum up all of values in the table here, which is equal to 5 over 36. All right, that's not too much like difficulties here. And we'll consider another topic called a marginal probability mass function. And this is just guided by the previous example, like we see here, S, because we are only consider S, or we only consider M, given a single jointed distribution. This might even think, well, we already know by the previous cases, but this is in a different context. So previously we know S, we know M, and we want to find a joint distribution. But in some cases, we're not giving any information about S and M. We're just giving information of this joint distribution of S and M's, and we know its table. So so consider here. What about if we are only giving this table about some other variable that we don't know? So we cannot say anything useful about M and S regarding this graph, but we can do a simple analysis to figure out, like to sum up all of the columns and all of the rows values of it, and we can deduce this one and this one, right? And we sum this up to be 1, and we sum the column up is also to be 1. So how can we say what happened in this case? We just get a marginal probability of PS and PM by summing over the columns and the rows of the joint probability mass function. So why we call it marginal? Because it's just regarding S, not M, or just regarding M, not S. So it's like we are just counting the marginal value, summing them up. So by a rigorous definition, it's like the marginal probability mass function is a so yeah, it has continuous version as well, but here is discrete version. So the joint probability mass function, they can write in this way. Like if we are only consider marginal, in this case it's 2-dimensional, but it can be n-dimensional. So in this case, we want to find the probability mass function of 1 to k. So if we want to find I1 to ik, what we need to sum. So in this case, seems like when we want to find S, we sum the value of n. And if we want to find the value of m's marginal distribution with sum of S, which is just the opposite. So it's intuitively to think about, well, we are just summing the value which is in the complement set of the indexes. So the index, if we consider the marginal I1 to Ik, we're summing up the index of the complement of the indices R1 to Ik, which is denoted as J1 to Jn minus K. And they're summing up their cardinality, summing up to be N. But they're just like the complement in the set, in the index set N. And some extreme example can be, we only want to know one of the indexes, and we are summing up all of the indexes not equal to I. We want to know xi is marginal regarding n dimensional. This is very likely happen in real life cases. We only want to know one factor's influence to it. And regarding all of the other factors, we just sum them up. So this is, we sum up all of the indexes j not equal to I here. I'm going to give a graph example about what marginal property actually looks like. So consider this is a two-dimensional cases and with discrete random variable. So let's say n equal to 2, which is in a R2 space, and x is equal to x1, x2 equal to yz. So the first dimension is y, the second dimension is z, and they may have finitely many values because they are PMF, so there are only countably many values here. Okay. And what is happening here? What is happening here is very, I would say, very interesting cases. It's like we're just dividing them into some shape. So in the first column, this is equal to z equal to 2, z1, z equal to z2, z equal to z3, and z equal to zn. And y maybe some other like elliptical shapes. For example, this might be y equal to y1, y2, y3, and they are just disjoint with each other. So this is yj. It's another elliptical shape y. Oh my god, this should not be connected. So this is y4, and this is yj. But we only consider yj. So regarding what I just write right now. So what we are gonna do here is to do a summing up of this value. Okay, so we write y equal to yj, and it's a union of yj, union from k to 1, k equal to 1 to capital N. And this is a very Germany style of N, I believe. Okay, so y equal to yj, and we just need to sum up all regarding all of the z here by the previous definition. So we just sum up k to 1 to n, and regarding y equal to yj by z equal to zk. However, in this case, this is our finding absolutely. This is our finding absolutely because in this case we're just taking a probability, and probability when they are in this case it's like we're only adding up that, so this can be put out to be p y j. But in this case, we might not indeed sum up all of it. We just need some z1, z2, z3, z4, because beyond that, it's just 0. So adding so much zeros in the trail is not very effective. And we can see some transformation formulas here. This is very similar to, for the single random variable cases, what's the expected value of some function regarding x. And this case is some function regarding x1 to xn vector, because there are multiple random variable. Okay, so the function is going from Rn to R. But I would say it can also go from Rn to Rn in a different dimension, or goes to Rn itself. But R is just to make us feel easy because it's one-dimensional, doesn't contain vectors anymore. So some cases, if we can use a function, a linear transformation, to make like some vectors Rn to shrink to one-dimensional. That's very useful. So if we define y equal to gx. Then py, which is this one, another notation, is equal to pgx equal to y. And this is when we consider like gx equal to y, is when consider all of the cases sum up that like the x makes when sum up all of the probability of x, that x make x gx equal to y. And we take the expected value of y, so like, well, we are summing up all of the possibilities and putting them into average. So we'll sum up all the y of PR as well. And in this case, we just plug it in here. And this is by the definition of expected value, right? Because PYY times y self is and sum up all of the values, the expected value. So here, what we will see is that we can retrieve this item out and put y inside. So it becomes something like that. And y, so what is y we define here is the gx. So it's actually equal to this one. And now we can see the outer two sigma notation. One is y, another is x equal to gx equal to y. So this seems like it's just sum up all of the x because we do sum up all of y and x is equal to y. So it's sum up all of the x. So this becomes sum up all of the x regarding gx and the probability of x. So this is why we derive this formula in the end. And one consequence of this property of this theorem 8.3 is we can use it to prove the linearity of the expected value. So let's give two discrete random variable with ex and ey. They're both smaller than infinite, which means they're finite. If all of the, and we take the absolute value to make sure it doesn't goes like a shape like that. It goes to multiple infinite cases. So if we take the absolute value, so it must like have a bounded above for that. So this is exactly what we want. And if they are absolutely finite, then ex plus y is equal to ex plus ey. And smaller, previously smaller equal to, and the smaller equal to cases, I think is when it's not the best measurable. The set x and y is not the best measurable, which is not sigma algebra. So in that case, it's not probability field. So in probability field, it's a sigma algebra, so it must be equal. It has the countably additive property, not a countably sub-additive property. So let's define here. Gxy is equal to xy. So we define a new function and use g in this theorem to deduce it. Okay, so exy is equal to we sum up all of the gxy and pxy, right? Probability of xy. This is by the consequence of this formula. We can see it's here. And because it's two values, so it just summing up one, it's just summing up x and y. Okay, and what happened? What happened next is like, because gxy is equal to x plus y, and we can just write it as x plus y. So here we might write one more step is equal to xy, right? So it's x plus y. I know, maybe not write this way. Like we can write it as xp plus yp, and p is this one. Okay. And then we can, because it's sigma, it's just adding them. So we can just adding them separately to put x here and y goes here. And later, because here only have x, not y, we just drop the y. And here we drop the x because there are no x. And finally, look at the shape of this one. This is just this is just the expected value of x. Similarly, this is the expected value of y. So we prove the linearity of the expectation. Okay. I think that's roughly the topic of the joint distribution of discrete random variable. And probably we'll see another type which is called continuous random variables joint distribution in the next lecture. But now we are talking about independent random variables. So random variables independent if the probability of x1 belong to some set, some sample space, subset of sample space, to xn belong to some subset space of sample space. They are equal to the summing up of all of the probability here. And this is this is a extended form of the definition of independent we see before, like x has equal to a, y equal to b is equal to probability of s equal to a times p s equal to b, and the pi sign here just means the time them all together. So this is our definition of independence. But if we want to apply the definition to any collection of random variables, whether discrete, continuous, or mix of both. Some cases like there are some variable discrete, but some other random variable which is continuous. And we'll use some method to figure it out. So first lemma is that the random variable x1 to xn, they're independent if and only if the events x1 belong to I1 to all of the events xn belong to In are independent for all intervals I1, In belongs to the set R. So this is a if and only if relationship. So if we're gonna prove it, we are gonna prove it in both directions. Okay. And what this means is like, but before proof, we might need to think about what this sentence really mean. So, so which means like regarding not just for all of the subsample spaces in R, no matter what subspace we pick for x1 to xn, we just need them to be in R, just need them to be in the overall sample space, and it should be all independent for each random variable, single random variable. Okay, so proving from this to this one might be pretty easy. It's just like we suppose them are independent at first. Then by definition of the independence, their how to say, their intersection with each other, the probability is just like the multiplication of each single event, which is to say, and this one is similar to x1 belongs to I1. And this is the definition of this one. So if they're just equal to each one, then all of them are independent. So this way is pretty easy. But what about the opposite way? So first we define x1 to xn to be independent. Then we need to figure out those events are independent. So we just define some events here, like AI equal to this one for all of the cases here. Then we just want to show like if they're like I just forget the word. What's it called? Intersection, yeah. So if A1, A2, A2, AK, their intersection, the probability of their intersection is just equal to their multiplication of the probability. So they'll be the same. If they're the same, then it's independent. So we'll use another strategy to prove it. So first, let I is inside some sets. So first define a overall index set. Not index set, but just like a random set, capital I is equal to R. If like I is in the set of this one, which is in the complement of the set we want to find. Then this one, we sum up this one is equal to this one, because beyond that it's just equal to 1. The probability is equal to 1 because it's R. As all of the cases consider R divided by R, the cardinality is still the same. And here we'll see, so in this case, AI, what's AI means? Just like xi belong to I1, and they are equal to this one by the definition of their independence. And this one is equal to this one by the definition of AI is denoted by this one. And roughly we will figure out this one because all of the index beyond k and below n, they're just 1. So the multiplication will not affect anything. We just draw them out. And this we find out this one. So we proved it in this way. And we proved both direction, and this lemma makes sense if and only if. Okay, and we'll see some other properties. The discrete random variable x and y are independent if and only if this one, which is a smaller case of the general case before, because the general case says all of the cases is going from xi to xn, and there must be independent. But here it's just like, well, we just consider 2 random variable, x1, x2, and y here means x2. Okay, and we need to we need their joint distribution, joint PMF equal to each of their PMF to multiply with each other. So in plain English, it means like the joint PMF of 2 independent discrete random variables x and y is equal to the product of the marginal probability mass function of x and y. Yeah, we need them to be independent, and we just time their single PMF. And because their single PMF is just equal to the marginal PMF when we deduce from the joint distribution. And the generalization is like that. 2 becomes n dimensional. And another generalization is like if there's a map going from R to R for all of the, maybe Rn to Rn as well. Like they're taken from all of the x1 xn to f1 x1 to fn xn. They're independent too. Just need the original random variable to be independent, and the map is going from the same the same dimension. It's going from R1 to R1, R2 to R2, R3 to R3. And here let's introduce one interesting topic, which is called random variable IDD. So what is IDDs? Independent and identically distributed. So it must satisfy 2 conditions at the same time. First, we need to prove that they're independent, which means which satisfy we say the generalization here, satisfy this one. And this one in general, as we see in maybe in the 3rd or 4th lecture, we see the independence between 2 random variable or 2 events. We say, well, it's very hard to prove the 2 events are actually independent. But for the random variable, it's truly very hard to prove its correctness as well. It's usually given by intuition. And this is just like a theoretic view of it. So to see they're independent, usually we just deduce by our mind, or we assume it's independent, or by common knowledge, like the coin flip is usually independent. And they have the same distribution. So a very easy example is a sequence of rolling dice is IDD. Because as we can see before, if you roll 2 dice, the second dice their numbers rolling up is IDD with the first one. So that's the definition of IDD, independent and identically distribution. So, okay, so there are some proofs, but yeah, we might be interested to see some of them. So here we can see why this is true. All right. The proof is, I think it's not including any useful steps. It's just given by definition x equal to x, y equal to y. So there, this by definition, this step by the definition of lemma 8.5 here, which is also by definition. And we just write it in this case, we just write it in a marginal probability, which you write in this way, another way to write it. So just get the result. Okay, and this is another other way to prove it because it's if and only if. So this is the first direction, and this is second direction. And the last thing I want to talk about today is the sums of independent random variables. So let's say there this is what we usually call a convolution, but I will talk about convolution several weeks later. When we just learn more about what real convolution is. So let's say here it's given a informal definition here. So x and y are independent discrete random variables. It doesn't say it's IDD, it's just independent, and with PMF P and the Q. So it's not IDD here because if it's IDD, it's identical. So this PMF X, if it's P and Y must equal to P. So here it's just independent. And the random variable z equals to x plus y has PMF here. So z is equal to x plus y. So how can we denote it? So we just write a function rz, and it's equal to the summing up of all of the x belongs to some set, and xy px times q z minus x. I remember here y is equal to z minus x, so probably this means y. And here y belongs to x, all of the y is equal to p z minus y, which is x and qy. So why this formula is very useful is because it's lead us to consider if there's a summing of different random variables, we just need to write it in a multiplication form by summing up the only one of the one variable into it, and the other variable we just use difference, like here. A difference between z and y is x, and difference between z and x is y. And we use the difference to deduce the other dimension of it. Okay, and the proving strategy is like, so how can we prove this one? We just prove it by using, let's see, using by the independence property. So x plus y equal to z. And this event we are gonna show is actually equal to some is equal to the union of all of the x equal to x, y equal to y, and x and xy is their sum is z. And this is by definition. And all of the x and y are destroyed by the definition of like all of the single event in the PMF's sample space. They're destroyed. They're destroyed points in the sample space. So let's see. This is our because x plus y is just equal to z. So x plus y equal to z is the PMF. This is PMF function. So all of the PMF function is regarding as this one. This is because this event is just this event, and the probability taken out can be moved in. And y can be written as z minus x. So it's just like summing up of x equal to x to y equal to z minus x. And in this case, it's p x equal to x times p y equal to z minus x, because x and y, they're independent, so it can be written in the multiplication product form. And notice that this form is already the marginal distribution, so it's pxx. This is the q, this is the q z minus x, because q is the PMF of y, and this is the PMF of y when the realization or the outcome is just equal to z minus x. In this step, well, this step is given by the independence of x and y. They are independent. And one interesting step we just not very see it before is from this step to this step. So why they can go very smoothly is because here we sum up the two dimensions x and y, they're plus 2z. But here we just use this condition here. We just separate this condition into our expression of the probability distribution. So in this case, we are just let this condition go here, and we sum up all of the x that have this property here. So it's I would say it's also can be called a transformation of it, a transformation of the condition from the addition to the probability event itself. Okay, and that's roughly for today. And the next lecture we'll talk about so this is a discrete version of the joint distribution. And the next lecture, we'll talk about the continuous version of multiple random variables and their joint distribution and joint PDF, which is probability density function.